On to part two, unit vectors and adding vectors by components. So we talked about vector notation already with the x and the y components of vectors, as well as the angle notation. But we're going to talk about how to write unit vectors next. So a unit vector has magnitude of exactly 1 and it points in a particular direction. It lacks both dimension and unit. It's only used to specify the direction. So unit vectors in the positive directions of x, y, and z axis, we label them as I hat, j hat, and k hat. So x is associated with I hat, y is with j hat, and z is with k hat. And we call this a right-handed coordinate system. So x and y, and then z is like this as well. We're also going to look at maybe not in this particular lesson, but there is a three-dimensional graphing calculator that you can access on Desmos that will help you to determine where these vector locations are when we're using these three-dimensional unit vectors or three-dimensional vectors. Unit vectors are useful for expressing other vectors. So we can express A and B. We can say vector A is AXI hat plus AYJ hat. So that's just another way that we can say this in unit vector notation. So if the book asks you to write something as a unit vector, make sure you're writing I hat and J hat associated with that. Same for vector B, same notation. Again, these are vector components of A in unit vector notation. So AX, I hat, AY, J hat. These are vector components. The AX and the AY, these are scalars, and these are the scalar components of vector A. We also just call them components. All right, so to add vectors in component form, we use the following rules. So we can say that the R component for, or the X component for vector R is AX plus BX. The Y component is AY plus BY. And the R component is AZ, or excuse me, the Z component for R is AZ plus BZ. And we can add these to find the vector sum. Sometimes vectors are expressed that are not in a way that's not parallel with the X component or Y component. That's not very common, but it can happen. So sometimes we can say we can shift the X and Y axis so that this is now X prime and Y prime, and it's shifted. And the only reason that we would do that is so that we can make generalizations about the X component for A and say that it's going along the x-axis. It's easier to make calculations sometimes when we change the axis to be at an angle. I think most of these problems are best when we go over examples. So here is an example: searching through a hedge maze. So this maze is formed by these tall rows of hedges. And after you get in the maze, you look for a center point and then for the exit. So here's where you'd start. You look for center point, and then you're trying to leave the maze. This figure shows the entrance, and it shows the two choices that you make at the junctions in moving from point I to point C. We undergo these three displacements as indicated in the overhead figure. So the best way that you can solve these is to draw out the vectors yourself. So they're going to show you a diagram like this, or they might just tell you the angle of the vector. Most likely you'll get some sort of a picture though, or a general idea, and then you'll want to translate that into the vector components on the XY axis. So we're going to look at these different displacements. They give us some information. They say that displacement number one, or D1, vector D1, is 6 meters and it's at an angle of 40 degrees. And that's theta sub 1, and that's right here. D2, they tell us, is 8 at an angle of 30 degrees for theta sub 2. And note, this is 30 degrees here. And for D3, it is 5 meters is the displacement for the vector. And that's at 0 degrees. Now that's helpful because that's going to be right on the x component. It's just going 0 degrees. So it says the last segment is parallel to the x-axis. So that's D3, and that's a good thing. That means we can just say that's dx is equal to D3, which is equal to 5. When we reach point C, what are the magnitude and the angle of our net displacement from point I? So our net displacement is going to be the total of all of these displacement vectors. Our net displacement, we can write it as adding these vectors. Vector 1 plus 2 plus 3 is our total displacement for vector D, our net displacement. Now to do this, we have to sum up the x components and the y components in a very similar way that we did from the last example with the airplane example. Finally, we construct the net vector D from its x and y components. So this should be a bit of review because we've gone over how to do this previously with cosine and sine. So we'll go through this a little bit quicker now. Cosine theta is adjacent over hypotenuse. So that we're going to call this D1x. Let me go back a slide here. So from here to here is D1x. So because D1 just goes from here to here. So from I to this point here is D1x. So I label that D1x. Cosine theta is adjacent over hypotenuse, D1x over D1. And then cosine theta is 40, it tells us for that one. We just plug in these numbers, times by 6 on both sides. We get D1x is 6 cosine 40, which is 4.6 meters. So D1x is 4.6. For D2x, this one's a little bit different. We have to use sine for this one. Sine of the angle is opposite over hypotenuse, D2x over D2. So that's D2x is what we're trying to find. We know the angle of theta sub 2 is 30, and we're going to say sine 30 equals D2x over D2. They tell us D2 is 8, so we plug in 8 there. Multiply by 8 on both sides, we get 8 sine 30 is equal to 4 meters for D2x. And finally, for D3x, D3 is equal to D3x because it's only on the x-axis, or it's not on the x-axis, I should say. It's parallel with the x-axis. And so because it's parallel, it's the same angle, or it's an angle of 0, and we just say that D3x equals 5. Now we sum those together to get the net total of D in the x direction. So it's 4.6 plus 4 plus 5 gives us 13.6 meters in the x direction for D. Now we're going to do the same thing for y. D1y is here. Now, this gets a little bit, sometimes we have to be careful with the positives and negatives here, but we'll get to that if we need to. So sine theta, we're going to look at our theta 1. I should have put theta 1 here, but that's okay. So sine theta 1 is opposite over hypotenuse. So opposite is D1y over D1 is 6. So now we have sine 40, the given angle, equals D1y over 6 times by 6 on both sides. We get D1y as 6 sine 40, or 3.86 meters. Now we're going to look at D2y. Now D1y is actually going up because D1 is increasing in the upward direction. So D1y is going up in the positive direction. And that's why we get a positive number, 3.86. Now, when we look at this, this gets a little bit confusing because D1 and D2y, they sort of overlap. And that's why I wrote them in different colors here. So D2y is in blue and D2y is going down because D2 is also going down. So now we're looking just at this triangle here. And really, we're looking at this as our triangle. This is the base of our triangle here. So cosine theta is adjacent over hypotenuse. The adjacent of theta sub 2 is d2y. And we're going to say over hypotenuse, which is over d2. d2 is 8. And we're repeating many of the same processes. So we're just going to times by 8 on both sides. We get d2y is 8 cosine 30. And it's 6.93. Now, we got a positive answer. But this is very important. The vector is going down. So d2y is a negative 6.93 meters. For d3y, in the y direction, d3 is not moving at all in the y direction. It is only in the x direction. So dy3 is 0. There's no vertical component at a 0-degree angle. So now we're going to add up the net total for the vector d in the y direction. 3.86 minus 6.93 plus 0 for the d3y. We get negative 3.07 meters. Okay, so now we've got this overall net vector for d. So the net vector for d is going to go from I to C. So that's the net vector, or our vector, we can call it just d net. And so if we redraw this diagram, we can now get rid of all of these zigzags and D1, D2, D3. And now we just have, here's our net vector D, and our net in the X direction, which we calculated was 13.6. Our net in the Y direction, which we calculated is negative 3.07. And we can calculate this with the Pythagorean theorem. Very simple formula. We went over it in the last video, and it's a very simple formula. We're just plugging this in. This is the formula for the net of a vector. This formula also applies if you have x, y, and z. So if you have a z component, you can still use this same formula. And so we get the net vector is 13.9 meters. All right, it says, what's the magnitude and angle? So we found the magnitude is 13.9 meters from point I to point C. Now we just have to find the angle, and that's not too bad to do. For the angle, we have to find tangent is opposite over adjacent. So that would be the opposite of theta is d net y. Adjacent is d net x. So it's d net y over d net x. We're just plugging those numbers in. D net y is negative 3.07. D net x is 13.6. And we get, I shouldn't have wrote an equals like that. That's not technically proper notation, but this is the proper notation. So let me fix that real quick here. So instead of writing that, I should have written it like this. Like, so we think of it as inverse tangent and inverse tangent of that value. Now I wrote equals, but that's what this part equals. So we're finding inverse tangent of negative 3.07 over 13.6. And that's the 0.2257. That's where that number comes from. And I might need to double check this in just a moment here. This is going to be negative 3.07 divided by 13.6. Yeah, so needed to, this was also supposed to be a negative there. So, but anyway, we get a final angle of negative 12.7. So that's how you plug in the tangent for that. Okay, next sample problem is adding vectors, unit vector components. This figure shows the following 3 vectors, and it shows it in unit vector notation with I hat and j hat. And so Really, it's just looking at kind of like where the coordinates of it are located. So at the very tip of A is at 4.2. Erase that. The very tip of A is 4.2 on the X and negative 1.5 on the Y. And the same holds true. The same rules hold true for B and C. And we want to find their vector sum R. And so to do this, we're going to sum all of the X components, AX components. Those are all the I hat components. So that would be 4.2 minus 1.6. And then for vector C, there's actually no I hat component. And I think they do that on purpose here just to make sure that we're being careful and looking at the notation. So can't add the i's because there's no i's for C. So it's just 0 and it's 2.6 meters for the X component for vector R. Now for vector Y, we do the same thing. We add all the j hat components together. And for that is going to be negative 1.5. This negative distributes to the j hat. And then 2.9 for the j hat and negative 3.7 for the j hat. And we get negative 2.3 meters for the y component for vector R. So that's how we add those vector components together. Now that we have those vector components, now we can start talking about vector R, which is this pink vector. And we're going to use our same equation. Essentially, the Pythagorean theorem. Vector R is the square root of the sum of the squares of the X component and the Y component of vector R. So we get 2.6 squared plus negative 2.3 squared. And we square root it and we get a value of close to about 3.5 meters. So that's for vector R there. A lot of these problems are multi-step problems, or they ask us a lot of different questions about the same question. And so we can also find the angle for this, again, using tangent. And for tangent, that's opposite over adjacent. So here's the angle opposite, negative 2.3 over adjacent 2.6. And we do the inverse tangent to figure out what theta is. And we get a negative 41.496 degrees, or about negative 41 degrees. All right, so that's it for this section. This is the workbook assignments as well.